Today, Academic Dad is going to be teaching you everything you need to know on solubility and solubility products. Now, what is solubility? Whenever you hear solubility, I need you to know that solubility in simple terms talks about the amount of a substance, be it in gram, be it in whatever unit, the amount of a substance that is contained in a particular solution. So whenever you have to think about amount all over volume, you know that what you're talking about is solubility. Whenever you have to think about solutes all over solvents, you know that what you're talking about is solubility. Whenever you have to think about solutes in 100 gram of solvents, you know that what you're talking about is solubility. That is why the unit of solubility is simply mole per liter. Once you know it, you're good to go. And you need to know that solubility happens to everything you can think about. Once you're talking about solution, when you have to think about the amount of this contained in this solution and all that, you know that you talk about solubility for it. But when you talk about solubility products, in simple terms, we know this as KSP. When we talk about solubility products, I need you to know that this only affects electrolytes. When you talk about solubility, you talk about it in terms of electrolytes. And this, you can also say it talks about ions. So when you are thinking about the amount of ions that dissociates, the amount of ions that dissociates in a solution, you now talk about solubility products. And that is why we have that this dissociation, for example, will be dissociation of positive or negative ions. And when you have this all over the solution, but you know that in most cases the solution is always constant because when it is saturated at that constant temperature, when you're getting the saturation, we now say that the reactant is always constant because in most cases this reactant is always a solid. So that is why we say that it's constant. And if that be the case, this gives us that since this is an ion, this is an ion, this is two amounts, so mole square all over the solution liter square. This gives us the unit of solubility constant. So you need to know that because this is always constant, we now have that KSP is always equals to A plus in this way and B minus all over AB. And you know that this AB is the reactant. So this is the reactant. This is the product. So in simple terms, solubility constant or solubility product is simply product over reactant. So once you know this, once you understand these basics, you are good to go. So you need to now know that if I have a solid that is in this form, that on dissociation, I'll have this to be A plus B minus this way, sorry. And that if I'm not getting the solubility product, I'll simply have A plus and B minus. It's supposed to be all over AB, but because AB is a solid, it's always constant. It's a solid. This is an ion. It's only the ion you take. So because this is solid is constant, we don't put it. So this is the KSP. Now the question can come, they ask you, what is the formula for finding solubility? This is solubility product. What is the formula for finding solubility? Now we know that if this is A plus, this is B minus, this is a soluble ion, This is also a soluble ion. So let's say that this is S and S for solubility. So which means that S square is equals to KSP. Are you understanding it? Is equals to KSP. KSP means solubility product. So if S square is equals to solubility product, to make S subject of the formula, we take the square root of both sides. So that this becomes S is equals to square root of KSP. And you know that this is the same thing as S is equals to KSP raised to power 1 half. So if you know this, this means that for you to find solubility when it has to do with relation to solubility product, this is the formula to use. So if you know this, I think we are ready to go to solving problems related to solubility and solubility constants. All right. So there you have it. As the question said, there's a question here. It said at 25 degrees C, the solubility of barium tetroxide sulfate is 3.9 times 10 raised to the power 5 mole per liter. Calculate the solubility product. Solubility product, that is KSP. So I'll write solution. I've told students most of the times when you don't know the answer to a question, just write solution. The minute you write solution, the answer will come. In Jesus' name. All right. Now the solubility, this temperature they give you, always know is constant. It's constant. That is what solubility is all about. It's always at 25 degrees C. Now the amount of a substance of solute contained in a particular solution in a 100-gram solution or solvent, usually at 25 degrees C. That's what solubility is all about. So if you know this, to solve this, it simply means that I will introduce the barium tetroxide sulfate. Now on dissociation, I will now have that I will get Ba. Now barium, whenever you hear Im, I need you to know that for most cases apart from sodium, whenever you hear barium, radium, you always think of it as a metal, and they always lose electron and they stay positively charged. Plus the sulfate SO4, you need to know this. On dissociation you get this. So this is aqueous, and this is a solid. So if you know this, you now need to know that for KSP, this will be Ba2 plus and SO4 2 minus. SO4 2 minus. And remember that the question gave us that this everything here is 3.9 times 10 raised to power minus 5, and everything here is 3.9 times 10 raised to power minus 1, because the 2, remember that this is what they gave us and they said it's carrying times 10 raised to power minus 1, 3.9 times 10. So if this is the case, it means that each one of these, the barium and this, contains this amount per mole, that is this mole per liter. So, and you see that they are in a 1-to-1 ratio. So if that is the case, when you multiply this, you get that the answer is going to give you 1.5 times 10 raised to power minus 9 mole square per liter square. So this is your KSP. So this is how you find the KSP. And notice that in this case, barium and SO4 2 minus, they are equal. This Ba2 plus is equals to SO4 2 minus, because one, the stoichiometric coefficient is 1, and they gave it to us as 3.9 times 10 raised to power minus 5. So they are equal. But there are situations whereby this could be greater than this. A situation whereby I mix barium chloride and I mix it with maybe sodium tetroxide sulfate 6 in water. When I mix such a when I have such mixture, or when I mix such ions, you see that in that case there will be displacement reaction, so that barium will displace sodium and then takes tetroxide sulfate 6, tetroxide sulfate 4, and a situation whereby the KSP happens to be greater than the normal KSP given to us here, it means that a precipitate is formed. But if it is lesser, there is no precipitate. So if you know that, let's move to the second question. All right, question 2 said, given that the KSP of radium sulfate, given that the KSP of radium sulfate is 4 times 10 raised to the power minus 11, he said calculate its solubility in sodium sulfate. I need you to know that if this is radium sulfate and this is the KSP, on dissociation you will have radium 2 plus SO4 2 minus. Now once you know this, check our video on electrolysis to know how to get all this dissociation. Now if you know this, it simply means that if this is the KSP given to you, that means that the Ra2 plus this is equals to KSP now is 4 times 10 raised to the power minus 11. This is equals to Ra2 plus and SO4 2 minus. This is equal to it. Now there's what we call the ice table. The ice table. This ice table, this means initial concentration. This means concentration. This means concentration at equilibrium, or you say equilibrium concentration. Now I need you to know something. If the coefficient here was, let's say 2, that means the initial concentration here will just be, let's say 2x. But since this is x and this is 1 and this is 1, this is going to be x and x. But because they gave us here that this is 0.10 m sodium sulfate. Now check something. From in radium sulfate, is there anything like sodium sulfate here? No. So this sodium given to us, we have no business with this sodium. This sodium, look here. This sodium, we have no business with this. Example, if they give us a question, they say NaF. Then they say calculate this one that happened in 5.0 mole of fluoride, F, the ion. Notice that since I have no business with this in the first one given to me, my only business will be on these two. So for that reason, I have radium and I have sulfates, radium and sulfate. Then here I have sodium and I have sulfate. Ignore what you don't have business with. Sodium is not found in radium sulfate. So this sulfate is already here. So the initial concentration I have is simply that radium is X. But this SO42 minus initially is X. Initially is X. But because they gave me 0.10 m, so it is going to be 0.10 m and not X. So the second part where I have the concentration here deals with the stoichiometric coefficient. So this is X and this is X. So at equilibrium, this is just X. This is X because this X is the same thing with this X. Then for this one at equilibrium, this is going to be X plus 0.10 m. But you need to notice something. Whenever you are given this initial concentration, and you look here, you see that this particular KSP raised to the power minus 11 is very less. So it is very, very low, which means that if you put it to be the X here and plus with this, it will still give you a value that is in 0.10 m. So for that reason, whenever you have initial concentration to be this, just take it that this is the setting as X and 0.10 m. So this is what you are carrying out. So if you know this, you remember that KSP is equals to solubility. Remember that KSP is equals to solubility and solubility, if you still remember. So for that reason, let me now carry this now. Radium 2 plus in this case is X, and this one is 0.10. So if you multiply these two, it simply means 0.10 x equals to, and the question gave us that the KSP is 4 times 10 raised to the power minus 11. So to get x, divide both sides by 0.10. Divide both sides by 0.10. Now when you divide this, you have x equals to This 0.10 is the same thing as 4 times 10 raised to the power minus 11 all over, this is 1 times 10 raised to the power minus 1. So when this crossover is the same thing as 4 times 10 raised to the power minus 11 plus 1. That is minus moving up. So that this becomes 4 times 10 minus 10 equals to x. So this is our final answer. So that means that the solubility of radium sulfate in 0.10 m affects the sulfate. It affects the sulfate. That means when a salt, a common salt, is found in another salt, it will decrease it. It will decrease the should I say the concentration, or do I say the solution? So that means this sulfate is affecting the sulfate in sodium sulfate. The radium sulfate is affecting the sulfate in sodium sulfate, so that we now get this to be minus 4 times 10 raised to the power minus 10. So I believe this is answer the solution to the question you have on your textbook. So you see this on your textbook. So this is the answer. This is how to go about it. So once again, remember to subscribe, like and share. Academic Daddy. I will be seeing you guys very soon. Love you.